Light, the essence that illuminates our world, has captivated minds for centuries. For centuries, Newton's view held that light was composed of tiny particles. This theory explained reflection and refraction but stumbled with other phenomena. Huygens proposed light as waves, akin to ripples on a pond. This model explained diffraction and interference but faced resistance due to Newton's influence. The early 20th century brought quantum mechanics, shattering classical notions. Wave-particle duality emerged, asserting that light and matter possess both wave-like and particle-like properties. This duality underpins our understanding of the universe, shaping the behavior of atoms, stars, and everything in between. Christian Huygens championed the wave theory of light. Huygens proposed that light waves propagate through a medium called the luminiferous ether. Huygens's principle describes how waves propagate, explaining diffraction. Thomas Young's double-slit experiment dealt a decisive blow to the particle theory. Young observed a pattern of alternating bright and dark fringes, explained by wave interference. Waves passing through two slits interfere, creating bright and dark fringes. Young's experiment firmly established the wave nature of light. This paved the way for a deeper understanding of light's behavior. The wave theory of light gained acceptance, challenging the particle theory. New observations hinted at a particle-like nature to light. Max Planck proposed the quantum hypothesis to explain blackbody radiation. Planck postulated that light energy is emitted or absorbed in discrete packets, or quanta. This introduced the concept of the photon, the fundamental particle of light. Albert Einstein explained the photoelectric effect, further solidifying the particle nature of light. Einstein proposed that light consists of discrete packets of energy, or photons. When a photon strikes a metal surface, it transfers its energy to an electron. If the photon's energy is sufficient, the electron is ejected. Einstein's explanation cemented the particle-like nature of light. The 20th century witnessed a seismic shift in physics. Quantum mechanics emerged, driven by the behavior of light and the atom. Quantum mechanics replaced the deterministic worldview with a probabilistic framework. Wave-particle duality became central to understanding the universe. The wave function describes the probability of finding a particle in space and time. Measurement collapses the wave function, forcing the particle to assume a definite position or momentum. Louis de Broglie proposed that all matter possesses wave-like properties. De Broglie's hypothesis extended wave-particle duality to all particles. The wavelength of a particle is inversely proportional to its momentum. Electrons, being less massive, have longer wavelengths comparable to atoms. This opened the possibility of observing wave-like behavior in subatomic particles. De Broglie's hypothesis provided a unifying framework for understanding light and matter. Electron diffraction confirmed de Broglie's hypothesis. In 1927, Davison and Germer observed a diffraction pattern in scattered electrons. This pattern was similar to those produced by X-rays, confirming wave-like properties. Thomson independently observed electron diffraction using a thin gold foil. These experiments established the wave-particle duality of matter. Electron diffraction revolutionized our understanding of the microscopic world. It paved the way for powerful tools like electron microscopes. Heisenberg's uncertainty principle is a cornerstone of quantum mechanics. It states that the more precisely we measure a particle's position, the less precisely we can know its momentum. This is a fundamental property of nature, not a limitation of our instruments. The act of measurement disturbs this system, introducing uncertainty. A wave packet represents a particle in quantum mechanics. A more localized wave packet implies greater uncertainty in momentum. The uncertainty principle shapes the behavior of atoms and the interactions between light and matter. Wave-particle duality underpins a wide range of technological innovations. Lasers harness the coherent nature of light. Laser light is monochromatic and coherent, arising from quantum interactions. Electron microscopes use the wave nature of electrons for high-resolution imaging. Scanning tunneling microscopes exploit quantum tunneling to image individual atoms. These technologies rely on the principles of quantum mechanics. Wave-particle duality has transformed our world, from medicine to material science. It continues to drive technological innovation and exploration. Quantum mechanics has unveiled a universe far stranger than classical physics. Superposition allows particles to exist in multiple states simultaneously. Entanglement links particles in an intimate and instantaneous way. Measuring one entangled particle determines the state of the other, regardless of distance. These phenomena challenge our classical understanding of reality. The quantum world suggests a universe more interconnected than we imagined. Exploring the quantum realm reveals profound beauty and mystery. The quest to unravel the quantum world continues. Physicists seek to unify quantum mechanics with general relativity. String theory proposes that the universe's building blocks are vibrating strings of energy. Quantum computing harnesses quantum properties for revolutionary computations. Quantum computers could transform fields from medicine to materials science. Exploring the quantum world challenges our understanding of the universe. The journey promises profound discoveries and a deeper understanding of reality. Wave-particle duality is a cornerstone of modern physics. It challenges our classical intuitions and expands our thinking. The journey to understand wave-particle duality has been marked by ingenuity and perseverance. The implications extend beyond theoretical physics, shaping our technological landscape. Lasers, electron microscopes, and other devices rely on quantum mechanics. Wave-particle duality continues to inspire and guide our exploration of the quantum realm.